And by 1988, I joined Shell as a drilling engineer, initially, again, on the rigs offshore. That lasted 7 years, and then I left Shell, went to work, well, initially for a drilling engineering service provider called ProDrill. That got bought by Smedvik Drilling and then by Deutag Drilling. And then by that time, I'd started in underbalanced drilling operations. By 1999, we started our own company doing coiled tubing, underbalanced drilling, which I did for 4 years. And then in 2003, I joined Weatherford as underbalanced drilling engineering manager in Singapore, in Asia, Southeast Asia. And that's where I started doing both underbalanced drilling, managed pressure drilling. First got involved in geothermal and air drilling operations. I then moved in 2010 to Scan Power Petroleum Technology to work on the Olga software. That got bought by Schlumberger a year after I joined them. So I was drilling advisor, well control, MPD, HPHT for Schlumberger, and still involved in geothermal wells even at that time. And then in 2014, worked for Wild Well Control as the engineering manager for Asia. And in 2017, I joined the current team of Modular Resources WellSpec, which is a Dutch company. And we do drilling engineering on advanced wells. So my geothermal history really started with air drilling in the late 80s in North Africa. That's my first exposure to air drilling. Then by 2003, once I started working for Weatherford, we were involved with air drilling and some geothermal operations in Indonesia. But in 2003, there was a distinct lack of engineering associated with the air drilling operations. The air drilling was done by the air team, so to speak, and it was all about pumping so much air. And when you start asking, well, how much air do we need to pump and why are we pumping what we're pumping, they didn't really have any good answers. So we started applying some engineering principle, especially after we had some issues, and then that also carried over to the geothermal wells in New Zealand, in Indonesia, and in the Philippines. And then in 2006, I also was involved in the work for Geodynamics in Australia on their hot dry rock EGS project, the Habanero and Julukia wells. That hot dry rock was hot, but it was never dry. I don't know who told them that rock was dry, but so I was involved in that, and then back again during my Schlumberger time, back to well engineering for geothermal wells in Indonesia and the Philippines, and now involved in 14 well campaign here in the Philippines, where I'm also living. So that helped through the COVID scenario by keeping me busy. So let's get started. Let me see if I can advance my slides. So I'm going to give you a slight overview of the reservoirs, the geothermal reservoirs. We'll talk a little bit about the well design. I think that's really where things need to come right. The aerated fluid design. I'll walk you through the aerated drilling equipment, so the drilling operations that we've done, and some of the data that we're now gathering in the drilling operations, some lessons learned. And I'll finish off with some engineering challenges, maybe for the students. If you think that all the challenges have been resolved, especially in geothermal, there's still a lot of work to be done and a lot of things to be solved. And then we'll We'll do some questions and answers, and hopefully some answers, but ask some questions. If there's any other questions later on, feel free to email me, and I'll give you my email address. It's on the first slide. I'll send a copy of the slides out as well after this is done. So feel free to contact me if you have any further questions or email questions. Right, so the geothermal reservoirs. We've basically got a layer of volcanic rocks, which are overlain by caprock, and that caprock in most cases, certainly here in Asia, is just sedimentary rocks. That caprock varies in depth. Here in the Philippines, where we're drilling at the moment, this is pretty thin. It's 1,000 to 2,000 feet thick, so it's not all that huge. That's then followed by volcanic rocks, in which we have the top part is the so-called steam zone, and then the lower part of the volcanic rocks is water and brine. It then again goes into, it's not really impermeable bedrock, but it's a drier zone, and it's the bedrock zone. And then the magma source, the heat source, is normally the volcanic rocks, not too far below that. So the targets for the geothermal wells are in these steam zones and brine zones, in these lower parts of the reservoir. And that's what we're going to be talking about, is how do we drill these wells, and what are some of the challenges that we're encountering in these wells. So we've got about 7 reservoir types that we can distinguish. Obviously, the single-phase water reservoirs, the single-phase steam reservoirs, the two-phase systems, the saline brine systems, and then systems with magmatic heat transfer and single as well as dual porosity systems. And just to go back to some of the physics, the phase diagram of water as well as the heat diagram, the enthalpy diagram of water, becomes very, very important in these geothermal drilling operations. And the understanding of what happens to water during the drilling operations is something that it really becomes important. So obviously we have our triple point where it's water and ice, normal freezing point. We have our boiling point at 100 degrees C, 212 degrees Fahrenheit. And then we have our critical point at 374 degrees centigrade. And looking at the heat transfer, the enthalpy of water, as the pressure increases, that enthalpy, the heat, the amount of heat stored in the water increases up to the critical point. And then it sort of gets to its maximum of saturated steam at these 230 to 237 degrees centigrade. And with that enthalpy diagram, we can also classify the geothermal reservoirs. And I really like the classification that was proposed by Sanyal of thermodynamics, in where we classify these resources, and that's becoming even more important now with people trying to find these enhanced geothermal systems in the deep geothermal wells that are being done, certainly in Europe. In Asia, it's all hot, as we will see, hot wells, but some of the newer geothermal operations where we go back into existing wells or deep wells that were originally drilled for oil and gas, we need to understand with the reservoir temperatures or the formation temperatures what sort of resources we have. So I really like this classification, and it gives a good idea of what the challenges are. So Sanyal has broken this down into 7 different classes. The class 1, class 2, and class 3 is what we basically call the low temperature systems. So below 100 degrees, it's basically water, and it's a direct use of that hot water to heat, to do space heating or other heatings. For greenhouse gases is very common in Holland, where we have a low, reasonably low temperature in these class 1s. The water gets circulated around and gets pumped back down. So this gives you also some idea of the power that can be generated with these different temperatures. Now, certainly here in Asia, in the steam fields, we're really in the class 5. Pretty much most of them are class 6 and class 7 steam fields. So we're up to 50 megawatts of electricity equivalent. And it's all steam and water mix or supersaturated steam that's being produced. And we're sitting in temperatures well over 300 degrees centigrade. Now, working in these class 5, class 6, and class 7 reservoirs, the well design and the engineering for the well becomes super important, just to make sure that that's all done safely and can be done, and the well can actually be drilled and completed. So the well design in Asia is mostly based on the Code of Practice for Geothermal Wells that's been issued in New Zealand. The New Zealand standard is widely used. The code of practice, the standard covers drilling, repair, abandonment, and some of the well intervention stuff as well, wireline, some coiled tubing operations, and some non-typical methods for maintenance of the deep geothermal wells. It doesn't cover anything above the critical point of water. It doesn't do reservoir engineering or environmental management of the wells or any equipment downstream. So it really concentrates on the wells and how we design the wells. And the well designs, there's a couple of different approaches to this. We have the New Zealand standard, which is based on the temperatures. Some people base it on the steam temperatures. Some people base it on the actual temperatures, and the boiling point in the reservoir or in the well is the other part. And we're really trying to design the well so that all the casing strings that get run and installed can actually contain the well and contain the steam as we drill the wells. So the wells certainly here in Southeast Asia in the geothermal reservoirs are pretty much andesitic volcanic resources in mountainous areas. They're some of the most beautiful locations in the world. You're generally close to a volcano somewhere and often in the middle of the jungle. And we have 2 distinct zones in most of these reservoirs. We have the overburden, anywhere from surface to 1,000 to 2,000 feet. In some wells, this is a little deeper. In Indonesia, we see overburdens down to 4,000, 5,000 feet. But then we get into this upper reservoir, which is generally the steam-filled reservoir. So the formation's heated, the formation's porous, it's fractured. And with the heat, the water in the formation basically becomes steam. So it becomes a pressure cooker, whereby the steam sits at the top and the brine, the hot water, the boiling water sits at the bottom. So the initial wells, the initial geothermal wells were all drilled in this upper part, in the steam part of the reservoir, and the steam was produced, and directly applied to drive electricity turbines. The wells today are generally deeper, and we're going after the brine, the hot brine, in the lower reservoirs or in the lower parts of the reservoirs. So we set casings in the overburden, a conductor, a surface casing to case off any unstable formations right below the conductor. We then set 13/3/8 casing at the top of the reservoir or in the top of the reservoir, drill the upper reservoir and case that off because we don't want to produce the steam anymore. We want to produce the brine. So in the Philippines, there's a layer of andesite that's non-porous that basically separates the steam zone and the hot brine zone. So the production casing gets set in that layer just above the brine zone. The brine zone then gets drilled, and that gets completed with a pre-perforated or slotted liner. And production is straight up the wellbore. There's no, like in oil and gas, there's no completions, there's no packers installed. The well is produced as it is, and it's turned on pretty much with the casing being the production tubing. We encounter drilling problems. They can set an intermediate liner, which is also slotted, and then drill a smaller hole section and run a secondary slotted liner, which is simply just placed into the well. It's not even secured. It's just hung into the well and left. So that's the design, the casing design that we're seeing most in use here, both here in the Philippines as well as in New Zealand and in Indonesia. So some of the challenges, and I've basically laid down some of the pore pressures that we can see. The green line here is the pore pressure in Indonesia. So we see basically very low pressures in the steam zone. And then once we get into the brine zone, that pore pressure pretty much follows a hydrostatic, a water column hydrostatic, but it starts much deeper. And if you project this forward, you see that the water level in these wells can be some way down, and there may not be any water until you're at the bottom of the steam zone. In the Philippines, the water level is down, but it's not as deep as in Indonesia, and the pressures are a little higher. And we see that the steam zone definitely has an effect on lowering these pressures, and then we basically go again into the hydrostatic brines with the pressure profile. The hydrostatic pressure is shown, and that's basically the water pressure, not accounting for the temperature, because this obviously with the high temperature that comes down somewhat due to the density effect with these high temperatures. The temperature profile is something that surprises most people, certainly people in the oil and gas industry. In the oil and gas industry, we're drilling HPHT wells, high pressure, high temperature wells. As soon as the temperature is over 300 degrees F or 350 degrees F, it's called high pressure, high temperature. Over 400 degrees F, it's already called ultra high pressure, high temperature. And in the geothermal fields, we see that we start at surface at 80, 90 degrees Fahrenheit. It ramps up extremely quickly through the overburden, and as soon as we're into the volcanics, we're at 400 degrees, ramping up all the way to 600, 650 degrees F in the lower parts of the reservoir. So extremely hot wells, and the temperatures are a major issue in the well, as we'll talk about a little more. So the upper volcanic reservoir, the steam zones, is mainly andesite, diorite, tuff, and rhyolite, all these volcanic formations. The formations are generally fractured, It's not so much porosity, it's fractures, and that are the producing aspects of the formations. The sedimentary overburden, we have clays, swelling clays. We also have losses because the water level is down. So if we drill with fluid all the way back to surface, as we do in drilling operations, then with these low pressures, inevitably we get losses as soon as anything porous is encountered or any fractures are encountered. So that's why also we see a number of casing strings in that overburden. That's just to make sure we can deal with the losses. So the 20-inch casing at the top of the reservoir is to contain a full column of water. The 13/3/8 casing is then looked at for the steam. So we need to be able, we take the hydrostatic pressure, temperature corrected, which is a little bit lower than the cold water hydrostatic pressure. We then look at the steam gradient from that point onwards, whatever point we're setting that casing, and making sure that we can actually contain a column of steam from the TD of the whole section. Should the well kick and start producing steam, we want to be able to close it in. The overburden is basically what holds it. So we need to set casing at these points if we want to control pressures from a column of steam. So the 13/3/8 needs to withhold or needs to hold a column of steam from TD of the next whole section, and the 10 3/4 needs to contain the column of steam from TD of the hole all the way to make sure that we have well integrity. All the casings are cemented to surface, so all the surface casings are cemented to surface. The production casing is very often run as a liner, cemented, tied back, and the tie back is then cemented, which allows us to cement the complete casing string. And cementing is very important because we need to make sure that there is no water behind that casing that's trapped between cements, because as the well heats up, that water heats up, and it can actually build up pressure if it's contained and collapse the casings. The production liners are not cemented; they are slotted pipe. They're literally just lowered into the well and left, and stay there. So that's basically what drives the well design. So instead of a gas column to surface, we take the hydrostatic pressure, which is corrected for temperatures, then look at the steam, a column of steam, a hydrostatic pressure of steam instead of gas, to do our casing design. So some of the challenges: the overburden, it's sedimentary rocks. It's generally drilled quite easily, but with total losses, and trying to cement those losses is can be a real challenge. They're drilled with water-based mud, and the directional work, any directional work that's done is generally started in the overburden. So we'll kick off the well if it's a directional well. We'll kick off the well on the overburden, set an angle, a sail angle, and then very often keep that. Once we get into the steam zone, we're into the volcanic formations, and we see that they are abrasive with fractures and low pressure. So again, we get losses very, very quickly. As soon as we hit the steam zones, we get losses. And we won't be able to fill the well back up anymore. We drill with losses, and that's one of the reasons we drill with aerated fluids, is to be able to support and minimize those losses. As soon as we're in the steam zone, we also have to be aware of the well control aspects with regards to steam kicks. Cementing the loss zones is complex. It's pretty much impossible because the temperatures are extremely high, and we have the risk of the cement flash setting, and the fractures are fairly large in some cases, so it's pretty difficult to set to cure the losses and drill with returns. So generally, we drill with losses. Even with total losses, we drill ahead, and we'll talk a little bit more about that. But we drill to TD, run the casing, and then cement the casing. The brine zone, very much the same, highly abrasive, fractured volcanic formations. The brine zone generally doesn't have total losses. We have partial losses, not always total. Partial, they can be severe, but generally we regain circulation at points. And the production liners, as I said, are slotted or pre-drilled. The steam kicks remain a well-controlled concern, and that's something we always watch for. So some of the construction challenges, expansion and contraction of casings with temperatures. As the well is produced, the casings get hot. As the steel gets hot, it expands, so the well grows. The well expands upwards because it's not fixed at the top. Cementing these casings with the high temperatures is a big challenge, making sure that the cement doesn't set whilst we're still pumping it. Return fluids and downhole temperatures for tools is a major challenge. And then with aerated drilling fluids, as we will see, we're looking at what pressures can we get, and the hole cleaning with aerated fluids can be a challenge. From the well control side, steam kicks and well kill procedures with losses is something that we always need to be aware of. And hole collapse, not so much. We don't see that much hole collapse in the volcanic formations. We do in the upper zones, but not in the volcanic formations. So the surface casings are run, and then the production casing is run. And as the production casing is run, that this master valve, which is basically a large gate valve, is installed as this production casing is installed. And that gate valve forms part of the well. So the BOP will sit on top of this gate valve. The gate valve basically closes the well as soon as we're done. And that's an essential part of the well to control and to allow us to take the BOPs off and move the rig and install the flow lines. So moving on to aerated drilling. We're drilling with a mixture of water, fluid, and air. And the main reason we do this is to manage the pressures in the wellbore and reduce losses. We're pumping with water, so there is a need to have sufficient water on location when we're drilling these wells, because we know we're going to get losses. We know we're going to get total losses. So any drilling that needs to be done, any water needs to be able to supply water to the location as fast as we can pump it, or actually faster than we can pump it. So an abundance of water is required to drill these geothermal wells. Aerated was introduced in the early 80s, late 70s, early 80s was the first time we started aerating fluids. And it's a mix, this mix of air and water allows us to control the wellbore pressures. The fluid and air mix is pumped into the standpipe, displays down the drill string, and then returns up the annulus to the surface. We have a rotating control device, an RCD, that seals the wellbore and that directs flow to a separator, as we will see, where the steam is vented, or any steam is vented, and the air is vented. The liquid and solids are returned to the shale shakers, and then the liquid is recirculated. So again, hole cleaning, hole stability to some degree, and downhole tools are main concerns. Even with aerated drilling, we're always looking out for that. So you can ask, why don't we drill with straight air? Because that's a very low pressure, and the challenge here is that with straight air, we could drill with straight air. In these geothermal wells, we have no gas, so we can actually use air without risking oxygen and gas mixture and getting potentially explosive mixtures. But just drilling with straight air and hammers, which is a good way to drill hard rocks, is use the use of air hammers, but it's simply with the water and steam that's in the well becomes impossible. Mist is basically air with a small amount of water pumped into the well. And again, from a well control perspective, mist is simply not going to work. Foam, just straight foam drilling with air, surfactant and water. Again, the challenge with foam is that the foam chemicals and the high temperatures, the foam just doesn't stay stable at these ultra high temperatures. So foam drilling again is out. So that leaves us with aerated drilling, and that's just air and water. These other ones are from the underbalanced drilling world, the oil and gas world, where we can drill with crude or diesel or synthetic oils. In a geothermal well, that's simply not possible. We don't want to introduce any oil into these reservoirs. And drilling with straight water can be done, and that is done if we have limited fractures or no losses. We simply drill with straight water. We don't really drill with weighted fluids other than in the overburden. So air can be used in geothermal. There's no gas, there's no hydrocarbon gases encountered in these reservoirs, so air is safe to use. Lost circulation zone, to get returns back, would require cement plugs. Certainly in the lower parts of the brine zone where we want production to come from, we don't want to pump cement. We don't want to damage the productivity. We drill blind with total losses, and that's a change that's been made. We used to use air and increase the air to get returns back to surface. We've come away from that because we've had a number of stuck pipe incidents. If we increase the air and lower the pressure in the wellbore, we find that the cuttings simply come back out of the fractures as steam is produced, and we get stuck pipe. They're subhydrostatic, and they're not really porous. They're actually fractured, and these fractures can be massive. This is a picture of a core. So you see some pretty big fractures, and the fractures are bigger than this often. We certainly know that, because we can pump all the cuttings, all the solids from the well, and all the fluids into these fractures without plugging them. So how does it work with aerated fluid design? We have a liquid pressure as we're pumping liquid, and we start to introduce air into the liquid. As we increase the air rate, the pressure of that liquid column as we're circulating that goes down. So that's the behavior of the liquid as we start to inject air and increase the air rate. The pressure in the column goes down. But as the pressure comes down, as we inject more air and we're keeping the same liquid rate, the friction goes up because of the air that's now being introduced, and the velocities go up because the air starts to bypass and the air starts to act with the liquid. So we get two different pressures. The liquid hydrostatic or the static liquid pressure, as we're pumping this, comes down. The air is introduced, that brings the liquid pressure down, but it also increases the friction. So if we combine these two curves, we get this sort of wellbore pressure curve. That's the combination of the liquid pressure and the friction pressure. And we've broken that down into this first part, which is hydrostatically dominated, so that the height of the column is the dominating factor here. The hydrostatic pressure is the dominating factor. And then when we get into this friction pressure part, we get friction dominated. And in the friction dominated part, we see that a variation in air rate with the same liquid rate does not move the pressures very much. So when we're designing the well, we want to actually operate on this flat part of the well, whereby moving or changing the air rate a little bit doesn't vary the wellbore pressures a lot. And that's the multi-phase design that needs to be done when we drill these aerated wells. It also shows you that just increasing the air rate doesn't necessarily lower the pressure in the wellbore. It can actually bring it up. So depending on the size of the hole that we're drilling, we need to be aware that just increasing the air doesn't always decrease the pressure in the wellbore. So in the geothermal parts, we're concerned with two pressure boundaries. The pore pressure, we don't want to drill underbalanced and produce the well. We want to have the drilling fluid overbalanced, and we want to be overbalanced over and above that pore pressure because we want to avoid kicks. Inflow of formation water and resulting steam kicks is something that we definitely want to avoid. We want to sit below that fracture pressure, which with these big fractures and vugs is not always possible, but we want to lower that pressure to get away as much as we can from that fracture pressure. As we increase the air injection rate, we get a minimum rate, liquid rate that we need to drive any motors, and we often drill with motors because we drill directional wells. And we have a maximum flow either dictated by the motor or by the MWD tool. So these are the two parts or the four boundaries of the box that we can actually work in as we design the wells. That's what we do. We plan the fluid model for each hole section, and we use different liquid rates and different air rates. So we look at the air rates. We have an air package on location that can deliver a number of standard cubic feet per minute. And we look at flow rates, 4 different flow rates, and the formation pressures, maximum, minimum formation pressures. And then we can pick a spot of where we're overbalanced at close to pore pressure. So it's a multi-phase model that's run. It's run for different liquid rates and different gas rates. And we plot these out so they're easy to see. And so this is at TD of the 9 7/8 hole section. And we can say, okay, we want to pump at 600 gallons a minute with 1,500 scuff of air injected, and we should get a bottom hole pressure that's just above 3,000 psi. So that gives us our operational parameters in relation to the pore pressures. Now, we also need to make sure that our MWD tools and motors function using this two-phase flow. So we have a graph that calculates equivalent liquid volume, and that's simply the equivalent rate of the air and the water through the BHA. So it's the liquid rate of the water plus the air rate. We combine those two, and that gives us an equivalent liquid volume rate. Now, we have a maximum flow through the motor and the MWD tool, and a minimum flow rate. So again, we look at this and we say, okay, same rate, 600 GPM. If we use the pore pressure, fracture pressure at 1500 scuffs, we're sitting here, we're comfortably below the maximum, but we're at the top of the range of the motor. So we know that the motor will work very well. So that's a plot that comes out of the same modeling. The next plot that we look at is hole cleaning. We're drilling with air and water. So it's a thin fluid rheology. Solids are not suspended very well. It's turbulent two-phase flow, and we're generally drilling at 30 to 40, 50 feet per hour. So we have significant amounts of cuttings in the well. And we need to make drill pipe connections. So we need to add drill pipes, shut the flow down. And we want to make sure that the fluids get carried up from the bit to wherever the loss zone is. So liquid velocity is the parameter that's used to transport the solids, because the solids get transported by the liquid, not by the gas. And we're using a liquid velocity of 130 feet per minute. So again, that red line is the 130 feet per minute. We're at 1500 scuffs with 600 GPM, so we're well above velocity profiles in the well. The final part that we look at is pump pressures, because we want to understand how much pressure we're going to see when we pump this air and water mix down the drill string, because our booster compressor is rated a lot lower than our mud pumps. So the booster compressors are normally rated to 2,500 psi. So we need to be able to ensure that we can still inject air into the liquid rate when we're pumping the liquid. So the standpipe pressure is important, and we need to make sure that we can stay below that maximum booster pressure. So that's pretty much the aerated well design that we're doing for each well and for each hole section. So we have a number of these graphs that are presented at each hole section. We look at an optimum air injection and liquid rate and make sure that that works. So looking at the pore pressures and the hydrostatic pressures, these are some of the fracture data that's been captured, leak-off tests that have been done in the field, the red dots. And you see in the overburden, they're close to the overburden gradient. But as soon as we get close to that steam cap, those fracture pressures are almost at hydrostatic level. So we use the hydrostatic pressure of water as a boundary, and we then look at the pore pressure. Now, what we're trying to do is we're trying to design the pressure profile in the well so we sit above the pore pressure but below that hydrostatic pressure of water. So we're trying to be somewhere in the middle, a little bit closer to the pore pressure if we can for that whole section, and see what liquid rates and air rates we need. And we do the same in the lower hole section. So we're trying to be above the pore pressure, but below this hydrostatic pressure. So what are we using? Aerated equipment. We have 4 compressors, 2 boosters, and our mud pumps, and a geothermal separator. And I'll walk you through what each of these parts do. Water is pumped with the mud pumps straight from the mud pits, and then the air is produced by this compression package. The air and the water are mixed at the standpipe, so there's an injection point at the standpipe, and then injected into the drill string as per normal. So 4 compressors, 2 boosters. We generally run 2 or 3 compressors and a single sometimes a double booster. Most of the time we run 2 compressors and a single booster, so we have a backup system. Compressors delivered to the booster increases the pressure, and it's then simply pumped into the standpipe through a rig floor manifold. The rig floor manifold is necessary to make drill string connections. So when we come to make a drill string connection, we turn the air off. We don't turn the air off, but we bypass the air. So we bypass the air to the bleed off. We close this valve, and we then shut the mud pumps down. And we have float valves in the drill string to contain the air that's already in the drill string. Bleed off that last part, make the connection. We switch the pumps back on, open this valve, close this valve, and the air goes back into the drill string. Pressure relief valve there and the mist pump. I will explain what the mist pump does. That's simply to inject corrosion inhibitor and some foaming agent. Air compressors are direct drive helical screw compressors, 1,000 standard cubic feet per minute at 360 psi. Screw compressors are basically 2 worm screws that look like this. They interact, so the air comes in, the screws turn, and there's an oil film in that air compressor to lubricate the screws, but also to seal the air in. And as the screw rotates, that air gets compressed in each vein of these screws. So we have step 1, the air comes in, the air gets compressed, it gets compressed a little further. Step 4, it gets compressed a little more and then comes out the back end of the compressor. These things turn at high rate, and that basically compresses the air to about 300 to 350 psi. That 350 psi goes into a booster, and a booster is a piston compressor. So the air goes in at 300 to 350, 400 psi. It gets compressed further in these 2 cylinders, and that gives us a 2,500 psi pressure rating for the air to be injected into the standpipe. These boosters can be configured in 2 different ways: a single stage, so we can run a higher volume, but we get lower pressures, or double stage, less volumes, but at a higher pressure. So depending on what pressures we need, and we generally run at double stages, so we get to the 2,500 psi. Maximum volume, about 2,700 standard cubic feet at 2,500 psi. So the engine is on this part. The radiator you see here is to cool the air. The air gets hot as it is compressed. So there's a big radiator, 2 radiators, one for the engine, one for the air on the booster compressors. The booster compressors are lined up by the side of the rig. They're normally in a single line. The compressors and then the booster compressors at the back, and then it goes into the standpipe. The mist pump is a pump with 2 small tanks, 2 water tanks, generally 20-barrel water tanks, with a small triplex pump that pumps at low volumes, small volumes. And then this mixed water is where we add the corrosion inhibitor. That's mixed with this water that's pumped in by the mist pump. It's pumped in at a certain percentage with regards to the base fluid, and we add some foamer when we're drilling with aerated fluid. We add a little bit of foamer, and that's normally in the 0.5% by volume or even less, and that's just to break the surface area of the water and to make the air distribute better through the water. If you inject too much foamer, it comes back very foamy, and you have lots of issues on the return flow. if you got full returns to surface. So chemicals are injected. The foamer is injected with tech steam pump into this stream and then into the airstream and to the standpipe. The BOP is a little different in geothermal wells. So when we drilled the reservoir section, the master valve was installed, and that's on top of the production casing. The BOP is installed on top of the master valve. We have a pipe ram at the bottom, choke and kill line, just like in oil and gas. And then we have something called a banjo box, which basically diverts the flow to back to the shakers, the geothermal separator and the shakers. We have an isolation valve and a throttle valve here, 2 rams, the annular. The flow comes up here and goes out here, and that's done to prevent the hot temperatures from damaging the rubbers in the annular preventer and in the rams. The rotating control device, the rotating control head, is on top of the BOP, but it has an outlet, but that valve is generally closed, and we flow the well through the lower part of this to avoid exposing the rubber components in the RCD, the annular, and the rams to high temperatures. So that's what that looks like. The rotating control device is a device that allows the pipe to rotate and the pipe to move up and down with the tool joints. This is installed on top of the annular preventer, and then the flow line comes out of the BOP stack into this geothermal separator. Rotating control device is a low pressure device. It's 500 psi. They're low pressure devices. They're really only there to divert flow from the rig floor back into the separation system and back to the shakers. The geothermal separator is there to get rid of the air that's pumped in with the liquid. So the flow comes in the back end. It's actually easier to see here. The flow comes in here into the geothermal separator. This is basically an atmospheric separator with the chimney. It's just a big box with a chimney, and then the air comes out the top, any steam comes out the top, and fluid goes back to the shale shakers through this line here. It's on telescopic legs. It can be elevated to get the right angle for fluids to go back to the shale shakers. This chimney can be turned and can be made longer as well. So if we do see a lot of steam coming out, we can raise the chimney. Sometimes liquid gets blown out, so we have to raise the chimney, and we can point it into the direction of the wind. So that's pretty much the equipment that's being used to aerate the fluid. Now, looking at the drilling operations, we start aerating right from the top of the well. Now, aerating fluids in a 26-inch hole is complex because you have a high volume, you have a big hole, and you have very small amounts of air. So we try to do that to reduce losses. It helps quite a bit, but it's pretty challenging, I would say, in the big hole sections. Once we get into the smaller holes, the 17.5, we can already see that aerating helps. So we drill overbalanced, we get losses, and the air is injected. This is the ECD in the well. So you see quite a bit of variation, but you see how low the pressures get, the ECD get, as we drill the well. In the 12.25-inch section, again, losses pretty much straight below the shoe. This is the steam zone. We get losses here, and then, so this is actually the steam zone, the loss zone. We can see that because the ECD does not increase with depth. And then below the loss zone, we see that the ECD increases with depth as we measure the pressure in the wellbore. The 9 and 7/8 hole, we start drilling overbalanced. So this is pure water. And then as soon as we hit any fractures, we get total losses and, or at least losses, and the ECD then just gently increases as we drill deeper. And then it drops further as we get towards the bottom of the brine zone because the loss rates increase. As we drill with losses and have no returns, we start annular injection at surface. So we pump water into the top of the well, and that's simply to make sure that the cuttings keep going down into the loss zones and we don't get steam kicks coming back. So we pump water into the well at the top and we pump down the drill string. So again, measuring data, that's one of the beauties that we now have. So we use an electromagnetic MWD tool. So we get bottom hole temperature, gamma ray, and pressure all the time, transmitted back to surface and recorded. And we can then actually see and compare that to our model, which is pretty close. It's the model pretty well overlies this gray line of bottom hole pressure. So again, we see the pressures increasing slowly, staying pretty much the same throughout these loss zones. Then in the 9 and 7/8 hole, we start with water. As soon as we get losses, we see a big pressure drop. The pressure increases only very slightly and picks up a little bit. This part was interesting. We see a big jump here in bottom hole pressures, and we actually increased injection of water at surface. So we get a higher column of fluid in the well that gives us a slightly higher bottom hole pressure. The standpipe pressure kind of reflects what's happening in the well. There's a bit of variation because we're drilling with motors, and it's not always possible to correlate standpipe pressure to the wellbore pressures. But the LWD tools give us some good indication of what's happening in the wells with regards to pressures, and it's become a really important tool in the drilling operations to see where we get the losses, at what point the losses start, etc., etc. Temperature-wise, interesting. So we have temperatures of over 500 degrees F, yet return temperatures and bottom hole temperatures. So this is the bottom hole temperature in green. Sorry, in orange here is the PWD temperature. Green is the PWD. Orange is the return temperature. Sorry. So we see that the temperature profile in the well, as we get the losses, we're injecting cold water into the string pretty much all the time, and we can really control the temperatures of the tools. The tool temperatures do not get that high, even with these high geothermal temperatures. Now, running into the well after a trip, we do need to circulate to cool the tools down to make sure that tools don't overheat. But once we're drilling, the tools don't really heat up that far, and we're able to drill with these tools without special temperature requirements. Something in the oil and gas industry, with the circulation, that becomes a lot more problematic. But on the geothermal wells, we also have a cooling tower for the pits. We have the geothermal separator and the cooling tower, which helps us to reduce cooling of the return fluids. So some lessons learned. Aerated fluid losses reduces the loss rates and provides control of wellbore pressures. Hole cleaning is important. We need to always be careful what we're doing with the rates, both the liquid rate and the air rate. The loss zones still need to accept all the fluids and solids. If the loss zone doesn't accept the solids, you're going to get stuck. So stuck pipe and watching for stuck pipe is an important aspect. Maintain the air and liquid rates to keep the pressure stable. So we don't increase the air rate anymore. We keep the pressure stable. We got losses. Everything just stays the same. And we'll let the well tell us what's required. Annular injection helps to get that flow down and push also the cuttings into the loss zones. And tripping is done with annular fluid injection, again, to maintain fluid levels and ensure that the well doesn't kick. So some of the engineering challenges, the drilling hydraulics are okay. We can match the pressures very well with air rates and liquid rates. That's now pretty well done. The prediction of bottom hole temperatures and return temperatures is still a bit of a challenge. The thermal models remain a challenge to get that right at these high temperatures. So modeling temperatures in the well as we're drilling remains a challenge. And then the well control modeling is still something that we don't do. The oil and gas blowout contingency planning software doesn't do steam kicks, and we don't have any software that can do steam kicks. We're using software that was designed for underbalance drilling to do the correlations. The challenge with that is that with the losses, the fluid level drops. So we have to adjust the parameters for the potential drop in fluid level. So we're actually looking at what we can do with the software to make that more dedicated to geothermal drilling operations. The well control challenges are still something that needs to be looked at. The temperatures never reduce. If you do in geothermal wells, and I don't care which kind of wells you do geothermally, the temperatures never go away, and the temperatures affect everything: cementing, casing, downhole tools, and well control. It's all about the temperatures, it's not about the pressures. From well control perspective, understanding steam flashing. A well control incident, this is in Indonesia, 3 wells. There was a landslide that took the 3 wellheads off the well, and all 3 wells were blown out. So you basically get 3 geysers on location when these wells are blowing out, and trying to and cap these wells is a pretty good challenge because the steam comes out at high rates. And it's really no more than water flowing into the well and flashing as the pressure reduces, and the high temperature allows the water to flash into steam, and that blows out. There's no dedicated geothermal drilling or well control software available yet. And blowout contingency planning is something that still needs to be done. It's all based on oil and gas experience, and the geothermal wells are definitely not the same. So just to give you a flavor, we're in the jungle in the mountains. The pads are tight, generally pretty close, pretty tight, and the rig just about fits. Air compression is on the back end, the mud pumps. The rig is then here. Entry to the location is in the front, just a little bit of space in the front to do casing and pipe work handling. 2 wells on location. There's a well here, and there's a well here behind this with pipe works. So very often we're drilling on locations where we already have 1, 2, or even 3 wells, and we're just adding wells. So shoehorning the rig in and the rig equipment in, and making sure the logistics all work can be a bit of a puzzle. Zooming in on that, you can just about see a production well here, which is hooked up, mud pumps, cooling tower, and this is the air package here with the mist pump, 2 boosters, 4 compressors, some tool shacks, mid pits, and then up here, the rig. So with that, I'll open it up for any questions and or any discussions or any things that you want to know about. So thank you.
Okay. Excuse me. Thank you. Thank you so much. Thank you so much. Okay. That was a great overview of geothermal well construction. You talk about well integrity. You talk about different things, super interesting and super because we are talking about this in this class. I will leave you with Dr. Salehi.
Hi, Steve. Thanks for the presentation. I was looking forward to this, and it was very interesting, to hear about the drilling and well construction challenges. I have a couple of questions. So you mentioned about the well control. Is the operation for killing the well is similar? Is just using water and then using the same procedure that we use in oil and gas, or it's going to be different?
It's using water, but it's all about cooling the well down again. When if the well kicks, it basically becomes a steam flow, and it basically starts to produce, and it will do that. It's like a pressure cooker. If you close the well in, it'll build up pressure, and it will become steam. Now, if you're inside the well with the drill pipe, you just circulate cold fluid, and you pump down the annulus from the top to cool the fluid down as well to kill the steam. Then it works. But if you're out of the well, and we've had this, we pull out the hole at casing point. We close the well in to remove the BOPs. When you get the BOPs back on and you open the well up, you have to be very careful that it hasn't built up pressure and you get a big steam kick at surface. So yeah, it's not quite the same. It's not whereby you circulate out on the choke and hold gas. I mean that's what we do, but it's not a gas kick that you're circulating out. It's basically the steam that you're circulating out, and you need to get the temperature down to stop the steam from forming, to stop the flashing. Now, flashing is not something people understand very well, and it's the well control guys come to us and say, well, it's just water and steam. I'm going, yeah, but you can't circulate it out, because if you leave the pressures, you can increase the pressure, but it still forms steam. So some interesting aspects to well control in geothermal. It's no gas. There's a bit of CO2, very small amounts of H2S that we're seeing, but it's really about handling the flashing and the temperatures.
Has there been any occasion that you have to drill a relief well, or is it just by circulating you kill it?
No, you cap it or you circulate it. I mean, we have the master valve there that closes, but in the wells in Indonesia, when they blew out, when the wellhead fell off, they basically just stabbed into the well at the top and pumped cold water into it, just bullheaded it back. So that's what we do. We don't drill relief wells. That's
okay. And you mentioned about cementing. So is there like the class G or class H, and you add a lot of silicate as we do in here, or is it a different type of cementing?
No, it's the same. It's class G with lots of silicate and retarders.
Yeah, sure. And then you mentioned about this loss circulation thing. That's a pretty challenge. So do you add this common LCM material, or is it just the cuttings that you use?
Cuttings in the reservoir section. There's no LCM, but in the upper sections, yeah, we use LCMs. But it's whatever works. We use. You have to be a bit careful with LCM that it can withstand the temperatures. So.
Oh, of course, yeah. A lot of them they don't work. And then, how long does it usually take to drill any of these wells? Is it like a typical high temperature oil and gas well time plan, or is it shorter, or of course it depends on depths, but
it's shorter. The 10,000 foot wells we drill in 30-40 days.
Oh, that's very efficient.
Yeah, we drill 40 to 50 feet per hour, and it's literally just pouring stands into the well. It's They got it down to a fine art. What we did find is that the bits, rotary bits work, the tricone bits, the PDC bits don't. We have a hard time drilling volcanics with PDC bits. They just wear out and don't drill. And the rotary bits, we have to be careful of the rotating hours because the formations are very abrasive. So we pull the bits after 60 hours.
I mean, it looks to me a very successful operation you are doing, and they have this geothermal drilling here in Utah. They call Forge, the Frontier Observatory of Geothermal, and it takes them much longer to drill, and they have a lot of challenges, but they never thought of using aerated or managed pressure drilling, and I never understood why. Because the way you're explaining, it's very efficient, and you could tackle the loss question better. But I don't know, they don't know the practice, or if the rock types here could be challenging to do aerated drilling. That's would be interesting that they try.
Yeah, the air rating definitely helps with penetration rates because we've drilled wells with just water and they drill a little bit slower. That's the geothermal wells in Australia. I was involved with geodynamics and those wells, and drilling 2,000 meters, 3,000 meters of solid granite that's not really fractured is hard going. And then for me, that was really an opportunity to use air and air hammers and say, hey, you can do much more efficient drilling with air hammers. Then the fluid starts to come in because it's never dry rock. And yeah, then the air hammer doesn't work either.
Well, thank you so much. It was very interesting. I let the other people ask questions, but I definitely have a lot of questions, but I don't want to take your time.
Feel free to drop me an email or something like that. No problem.
Yeah, I will do that.
Okay. Any questions from the audience? Yes. Okay, yes, please.
Thank you so much, sir, for the wonderful presentation.
You're welcome.
Yes. Okay. So I just have some other questions here. So I was going to ask, like, if compared to sedimentary, volcanics tend to be harder. So, for some unfractured formations, when maybe trying to fracture them, I want to guess maybe higher pressure is used for the fluid used to fracture them.
Yeah, we don't fracture stimulate. The formations are naturally fractured. So we actually want the fractures. We can drill sections where there's no losses, and we just keep drilling until we encounter losses because we're actually trying to find the fractures because the fractures are the producing zones of the wells. So we don't fracture stimulate. We don't pump fracs. It's not a fracking operation.
Okay. So, so in what if I was thinking, what if in the case of maybe an EGS system where maybe two wells were kind of wanted to connect maybe two wells in an EGS system and the rock was not properly fractured? What would happen in that case?
You don't in EGS wells like that. You need the connectivity between the injector and the producer. So if you can't frac. And that's been the question. That was the challenge in Australia with the EGS wells too. You drill the first well, whether that be the injector or the producer. You then frac the well. You need to understand where the fracture swarm goes or where the fractures go. So you need to understand the spread of the fracture itself. Then you drill the second well, be it the injector or the producer, into the fracture swarm. But the challenge there becomes you've fracked the well, you've pumped liquid into it, you've created the fractures, now you drill into those fractures. And then what was happening in Australia was they were taking kicks as they drilled into the fractures because that water was now hot and had built up pressure. And the hydrostatic pressure is reduced because of the temperatures. So they were trying to understand, well, these wells start to flow and we don't understand why because we know we're overbalanced. I said, yeah, but your fluid density drops with these high temperatures. So drilling into the fractures is not easy. And if you drill both wells and then frack them, the question then is, can you make sure you can connect the two wells? So yeah, and that's something that they're struggling with in Europe now too. And that's the EGS wells are being looked at in Europe, and that's still a big challenge. In the steam fields in the Far East, we don't need to fracture. We produce from the reservoir, so it's a little bit easier. But yeah, I see the problem with the EGS, with the new systems with the dual wells. It's a bit of a challenge.
Thank you so much, sir. Thank you so much.
Any other question? Okay, I have two myself. The first one is you mentioned the cement jobs. It's top jobs. Okay, a complementary cementing in cementing operations, or they are just, for instance, you do the regular cementing and then you complement that with a top job.
Yeah, we do regular cementing and complement that with a top up job.
Okay. And my second question is, you mentioned that you use cement, but the cement, after certain temperature becomes unstable. What was that temperature, especially for foam, air, or nitrogen?
The foam is, I think it's only good to 200 something degrees C. I can't remember the exact numbers, but the foam polymers basically break down at high temperatures and it becomes just black. It doesn't, the foaming action stops. I mean, that's something we learned very early on. We do pump small amounts of foam into the well, but it doesn't look like foam when it comes back, compared to foam drilling where the foam comes back as white foam, as soap. In geothermal, it turns black because of the temperatures. The polymers or the chemicals just burn basically.
Okay, gotcha. And a final question is, okay, you mentioned that the wells are not the well design has not tubing, but is produced directly through the casing. So how that production directly through the casing affects the life, the time of the well life. Saying that when you are using a tubing, if the tubing is born, okay, you just retrieve that tubing and put a new one. But in that case, you have the casing. So
yeah, and that's a big challenge. So there's both scaling. There's a lot of scale built up in these wells. So very often you have to go back in and drill out the scale, and clean the well up. And there's significant corrosion at these high temperatures. So the casing wears out, and if the casing starts to fail or leaks, then it's basically P&A. I mean, I've not heard of anybody running smaller casing inside and doing that. So yeah, that's definitely an issue with some of the wells. But some of the wells, certainly here in Indonesia and the Philippines, have been producing for 20, 25 years. So, it does work. But you have to be very careful with the water that's being produced. They do a lot of analysis on the chemistry of the water and the gases.
okay, yeah, okay, that makes sense. Especially, complementing the cementing operations with top jobs, you need to assure that the cementing is perfect.
Yeah, it's making sure there's no free water behind the pipe that's trapped between cement, because as soon as that heats up, it basically just starts to build up pressure and it can collapse your casing. And then your well and that normally happens pretty quickly after you start producing the well, because it heats up, and then your well is done. As soon as the casing is collapsed, that's pretty much the end of the well. Sometimes they can sidetrack the well, they can cut and sidetrack the well and re-enter it, but it's not easy. It gets expensive.
Yeah. Okay, thank you so much. So I don't know if we have any questions from the audience here in the room or
like to ask
online.
a question.
Okay.
I'd like to ask
Yes.
a question. Can you hear me?
Yeah, go ahead, Robert.
Hey, Steve, this is Bob Davis. I'm a retired Schlumberger guy. I used to be based out of Jakarta and worked with geothermal operators there, and also in Bakersfield and China Lake and the geysers and down in the Imperial Valley. So our big effort was getting borehole image logs in these wells. It was a very important log. And of course, we burned up a lot of tools. Do you guys try to do any imaging logging?
No,
No.
we tell the geologists they're lucky to get cuttings back if we have returns, and they have to live with it. And if not, use the gamma ray to see what rocks we get. But
Oh, you
no,
guys take the easy way out.
no, we don't do image logs. I've never seen anybody try to do that. But that's the big challenge, getting
Yeah.
logs in these wells. It's just the temperatures are so extreme that you can't
Yeah.
even wireline them. By the time the
Yeah.
tool gets down there, it's destroyed.
It was tough. They used to put chillers on. I forget if that was in Indonesia or China Lake, but it helped. It wasn't 100%, but they chilled it down to where we could usually get a log sometimes. But anyway, the data was really helpful to them. That's why they were willing to go through the bother of doing it. So anyway, I just want to thank you. That was a great talk and so thorough. Wow, I learned a lot.
Good, thank you. Yeah,
Thanks a lot.
and getting logs is always a challenge. All the geologists want more data, but putting tools in the well is never easy in these temperatures.
Nope, and I was on the other end trying to get them to work.
Yeah, I
So
feel for you.
we can relate. So
Absolutely.
thank you very much.
Thank you.
Okay. Thank you very much, Steve, for your time, for sharing your experience, your knowledge. That was super, super instructive class, super comprehensive. So thanks so much. And, let's stay in touch. And, we really appreciate the time and, and your effort in this Tech Talk. Thank you so much.
No
Have a
problem. And I will send
Okay.
you the PDF.
Okay, have a good day, and thank you so much for the people that attend this meeting. And next week we are going to continue with these tech talks. Thank you so much, and have a nice afternoon and night.
Thank you.
Thank you. Cheers, Steve. Well done.